Hi, my name is Eduardo Ox, and I'm organizing together with a friend called Fernando Lucatelli a workshop called Logic for Children that is going to happen on the UniLog 2018 in Vichy, France. And this is Silana Ox, who is helping us with some non-mathematical things. Let me start with the why I started to become interested in this. Many years ago, I was trying to understand non-standard analysis, and I realized that some of the calculations that I was doing with infinitesimals, they could be done in a more simple setting, in which instead of using ultra powers, I would use just filters and filter powers. And the only way where I saw this being discussed was in topos theory, and I tried to read Peter Johnston's first book called just Topos Theory, and I found it incredibly abstract and impossible to understand, and I couldn't stop thinking, I need a version for children of this. And I realized that this was the key idea. I needed a version for children of many things in mathematics that I was trying to read, and I couldn't because it was very hard. And with time, this became a much bigger project. Among its subtasks, I'm going to discuss this once: to find the right definition of children, to develop a basic toolbox, and to make these things publishable. The right definition of children is, of course, based on how I function when I feel that something is too abstract for me, and I need to build particular cases and examples and test these examples and make diagrams and so on. To develop a basic toolbox would be to build some tools that I can reuse in many situations and give names to them and define them formally, and also make these things publishable. And the difficulty here is that we need to not only make these tools look formal, but we also have to find a way to make these things look non-trivial, because at first sight we are just working on examples. By the way, the opposite term of children, the default opposite term would be adults, but I prefer to use mathematicians. And the idea is that a mathematician is someone who feels that everything should be done as generally and as abstractly as possible, and doing otherwise is bad style. An example that I'm going to use later in the slides is that we're going to find the right adjoint of a certain functor in a certain diagram, and the easiest way to find it is by guesswork and by trial and error. The adult way to find it would be by using Khan extensions and a general general techniques that work everywhere. And one expression that I love and that I'm starting to use in my presentations a lot is this step or this argument offends adults. About the first task, I have a discussion of this. It is much more detailed, but it is elsewhere. Just let me give some ideas. The right definition of children, remember that children means people without mathematical maturity, is that children prefer to start from particular cases and only then generalize. Children like diagrams, and they like finite objects that can be drawn explicitly with all details, so that they can look at these objects and try to find patterns. And they become familiar with mathematical ideas mostly by calculating and by checking several cases, rather than by proving theorems, starting to prove theorems right away. For example, if we give to a child a box with pentominoes like this, and we drop all the pentominoes on the table, the first thing that the child is going to do is to try to play with pentominoes for a while, to try to find a way to tile the box again. And for them, it is much more natural to play with these objects for a while before trying to prove theorems about about strategies for finding and tiling and discussing game trees. About the basic toolbox, note that I'm starting with category theory for children, first because I'm a categorist, and second because category theory uses diagrams and generalizations a lot. Not very explicitly. Most books on category theory, they seem to be discussing diagrams, but most of the time the diagrams are omitted. Anyway, here are the 4 basic tools that I use most of the time. I call them parallel diagrams, positional notations, and internal views. We are going to use these 3 ideas and examples in a few slides. And there's also a 4th tool called archetypal cases that we are not going to use here. And the third task would be to find ways to publish this. Remember, category theory books treat examples very briefly, as if they were trivial. As if they were just exercises and homework. And one idea that seems to be working is that we can do things for children and for adults in parallel, and we can find ways to transfer knowledge between the 2 approaches. And this idea of transferring knowledge and doing things in parallel is sort of borrowed from non-standard analysis that uses transfer theorems between the standard universe, here, the category of sets, and the non-standard universe that is built as an ultra power of the category of sets. So we have theorems that let us transfer truths from this universe to this other one, and also from this one to this one. What we are going to see can be drawn in this form here. We draw the particular case at the left, we draw the general case at the right, and it turns out that we can do things in a way that the diagram here has exactly the same shape as the diagram here. So they are very easy to compare. We can use the particular case to understand the abstract notation for the general case. We can use it to see how to particularize the general ideas. And we can also sometimes we can also do something like this, which is to start with a particular case drawn in a certain way and then try to find the right generalization, or try to translate it to the general language and to use it as a dictionary of the standard notation. In the rest of the slides I'm going to show an example based on geometric morphisms, which is something from topos theory. I'm also going to give another talk at the conference in a workshop called Logic and Categories. The title is Visualizing Geometric Morphisms, and there I'm going to discuss sheaves and geometric morphisms. Sheaves are somewhat famous. Some people outside mathematics know a bit about sheaves, and they seem to like it. For example, some philosophers know a bit about topos theory and sheaves, but they don't have a very clear way to explain what they're doing. And these are 2 parts of topos theory that look incredibly abstract at first, and the techniques that we're going to see here are ways to make them less abstract. The trick that we're going to use here is to start with presheaves with very specific presheaves that are easy to visualize. We start with a very small planar category like this. I call it boldface B. It has 6 objects and 1, 2, 3, 4, 5, 6, 7 arrows. And now that we have chosen the category boldface B, we can draw a presheaf on it like this, and the presheaf is going to inherit the positional notation here. It's going to draw with the same shape as this thing here. But now this thing is a set, this other thing is a set, this thing is a function between sets, and so on. And the next step is to choose a subcategory of the category B. Let me call it A, and I'm going to choose the subcategory that is made of the middle objects and middle arrows in the category B. So a presheaf on A can be drawn like this. And the inclusion F between this smaller category and this bigger category, it induces a geometric morphism that we also call little f from the category set to A to the category set to B, And if we look at the details of the definition, the geometric morphism is an adjunction between two functors. We can draw it like this. The category set A is here at the left, the category set B is at the right, and the functor f with the star above moves to the left, and the functor f with the star below moves to the right. And it turns out that the functor that goes to the left, f with the star above, it is obvious in the sense that it is very easy to construct, it's very easy to define, anyway. And the functor f with the star below, it's a bit harder. We want it to be the right adjoint to this functor here, and the way that adults would build it would be to learn can extensions that work for many situations. But in a situation that is very simple, like the one that I'm going to show, the functor f with the star below can be built by a bit of guesswork and trial and error. Let me make a parenthesis and discuss what are internal views. The internal view of a function called square root that goes from this set to this other set would be like this. Here we draw the internal view of the set N, here we draw an internal view of the set R. Note that I'm not drawing all the elements of the set N. Here I'm drawing some very concrete elements, and here I'm drawing a generic element, little n. And in this case, the most important thing is that in this drawing, the internal view shows the notation for what this function does. And in this case, it turns an element little n, a natural number, to the square root of little n. And when we pass to categories, the things are a bit harder because inside the category C, we have objects like A and B, and morphisms like this morphism G here. And in this case, I'm choosing a generic object here, another generic object, and a generic arrow, morphism between them. And this diagram shows how, that this object is taken to an object that I write like this object is taken to this object here, and this morphism is taken to this morphism here. Note that the convention and the notation is to just precede everything with a big F. The next step is to erase the blobs. So this is an internal view drawn without the blobs. And let me go back to geometric morphisms. Here is an internal view of the geometric morphism F that I was discussing. Here is an internal view of a generic case in which the geometric morphism F would go from this topos here to this topos here. But I'm going to work on a particular case in which instead of taking an arbitrary topos here and another arbitrary topos here, I'm going to choose this category and discuss geometric morphism going from here to here. That is actually a functor going to the left, a functor going to the right, and an adjunction between them. And so this is a geometric morphism drawn for adults, and this is its version for children, in which everything is made much more concrete. I've defined the categories A and B elsewhere, and now the geometric morphism takes an object F that I can draw using the positional notation like this to something like this, that it's very easy to obtain. We just have to erase some parts of the original diagram. And the object G here, from this topos, F or set to A, is taken to a bigger diagram, and we have to complete the missing positions in some way. And it turns out that we can, it's not very hard to check that the right thing to put here on the top is the limit of this V-shaped diagram, and the right thing to put here in the bottom is the terminal object, which is the singleton set. And that's it. I just wanted to show an example. If you'd like to take a look at a page with lots of resources about the workshop and about the bigger project about doing logic for children, you can go to this page here. And let me just finish with a smaller copy of the main diagram. And that's it. Thanks.